So as promised, we're going to now use our techniques of solving first-order linear differential equations to solve the rocket launch problem with air resistance. So here we go. So it's the same rocket problem, meaning the rocket starts at ground level. It's burning fuel at a constant rate beta and ejecting exhaust gases at a speed c meters per second relative to the rocket. And the only difference is that now we are including air resistance of 5.4. The units of air resistance are kilograms per second, at least when we're talking about air resistance that is proportional to velocity. So we're going to make that assumption for this problem that air resistance increases proportional to the speed with which the rocket is traveling through the air. So we'll write and solve this differential equation and recalculate the height and velocity at burnout time tau. So the conservation of linear momentum says that the force acting on the rocket and gas is equal to the derivative with respect to time of mass times velocity, but now we have two forces acting on the rocket and gas. We have the mass times gravity, that's the force of gravity, and then we have the air resistance. And both of these forces are pointing down. They're working against the rocket. That's why there are minus signs. And K is the coefficient of air resistance, which we said is 5.4. So ignore that. It's not some constant. We know what K is. So we derived this equation in the last presentation. And the only difference is that now we have an additional force, which I've put in red. Everything else in our derivation stays the same. And you can take the limit as delta t approaches 0. This will approach 0, this approaches dv dt, and this approaches beta. So we have that. And again, mass starts at the initial mass and it's decreasing at a rate of beta, because that's how fast the exhaust gases are leaving the exhaust port. So we can replace m with m naught minus beta t. And it looks like I did a significant amount of simplification here. I moved a bunch of stuff around. Looks like I divided both sides by m as well. And so in the end I didn't do much. I just moved this over to the right-hand side, or to the left-hand side, sorry. And looks. So I just moved around a bunch of terms here to get this equation that you see here. And then we replace m with this expression, and we're left with this equation, which looks pretty complicated, but keep in mind k, m naught, beta, c, g, these are all just physical constants. The only variable we have here is v, and v is a function of t. And with that in mind, this is a first-order linear differential equation. So we'll multiply both sides by an integrating factor. The integrating factor is e to the integral of p of t, which is this here. E to the integral of k over m naught minus beta t, which simplifies to this. This is the integral, and then e to the log is just that, and it's still raised to the minus k over beta. So this, what we have here, is our integrating factor. Let's multiply both sides by it and see what happens. And we now have, when we recognize that the left-hand side is the derivative of I of t, v of t, the right-hand side is this now. we'll integrate both sides. The integral of a derivative is just the thing that was inside. And on the right hand side, we just use, it basically amounts to a u substitution of u equals m naught minus beta t. And when we integrate both sides with respect to t, it's just the u substitution, and then the power rule allows us to go from here to what you see here. And here's my constant of integration here. Multiply through by this so that we can get v by itself. And we have this expression for v. So this now gives us the velocity of our rocket as a function of time, t. Everything else are just constants. Notice that the rocket started at rest, so at time 0 the velocity was 0. And when you plug in 0 for v and 0 for the t's, you can solve for c1 and you get this value for c1. Just as complicated as it looks, it's just a bunch of constants combined together, and they give us the value of c1. And noting that velocity is the same as the derivative of y with respect to t, we can integrate this equation again, since v is dy over dt, integrate both sides, and we get y. So y equals the integral of this, which is this. Pretty formidable expression, where we know what c1 is. We already calculated c1, but now we have an additional constant of integration, c2. And then again, y equals 0 when t equals 0. That's an initial condition because the rocket started on the ground. So put in 0 for t's everywhere, and 0 for y, solve for c2. And this is our expression for c2. Pretty immense when you consider that c1 is all of this. So let me show you how we can use computers to make sense of these solutions. So these are what we got for height and velocity. And of course, velocity is just the derivative of height, or to say it differently, height is the integral of velocity. So we said that c1 is equal to this and c2 is equal to this. So here's what we can do with Mathematica. You don't have to plug stuff in by hand, per se. You can store all the constants as these replacement rules. So these are the constants that we were given in the problem. Lowercase c, that's the exhaust gas speed, was 500 meters per second. The final mass is m1. We actually didn't end up using the final mass. We just used the mass rate of exhaust gas release, which was beta. Anyway, these are all of our constants that we were given in the problem. This is our expression for c1. This is our expression for c2. And we just plug in the burnout time. This is tau. Tau we said was 10. The rocket finishes burning its fuel after 10 seconds. So we just let t equal 10. And when we plug all of these constants into these expressions, which are just this and this, we get the final velocity, 47 meters per second, and the final y value, which is 354 meters. This / dot constants just means take this expression and make the substitutions given by constants, where constants is this list of substitutions. And the same was done here. So our final velocity is this and height is this. You can take a look at what they were before. I believe the rocket went thousands of feet in the air when we did not take air resistance into account. So air resistance is clearly well, it can't be ignored. So here's a problem that's a bit of a mouthful to say. It's just kind of a really fun miscellaneous problem. It's pretty much just it kind of stands alone. The solution is just kind of clever, and I like this problem, so I'm including it. But it really doesn't have anything to do with rocket launches or first order linear equations for that matter. So suppose we take a 4-foot rope with 3 feet of it arranged like in a heap at the edge of a table, and then the last 1 foot is hanging off the table. And then suppose at time 0 the heap begins to unwind and the rope starts to fall off the table because gravity is pulling it down. We'll assume frictional forces are negligible and figure out how long it takes the rope to fall off the table. So here we are. Here's our rope arranged in a heap at the edge of the table. There's 3 feet of it here, and there's 1 foot hanging off the table. Please ignore this. I guess I forgot to animate it. My bad. Let x of t denote the length of overhanging rope at time t, and v of t will denote the velocity, where we're considering down to be the positive direction, because we want x and v to be positive. So when the rope goes down, we're going to consider it to have positive velocity. So x of 0 is 1, because we started with 1 foot of rope hanging off the table, but the initial velocity is 0 because the rope started at rest. And we also know that, of course, by definition, velocity is the derivative of x. The speed that the rope is going down is equal to the rate. Well, this is really just a definition. It's a tautology. So let rho be the linear density of the rope, so that the amount of mass hanging off the table is density times the length of rope, rho times x. So we have this much mass hanging off the table, and gravity is pulling on that rope. So the force of gravity is always mg. Since gravity is pulling down, it's a positive force in our coordinate system, rho g x, because mass is rho x and g is g. Newton's second law says that force, which we just agreed was this, is also equal to the derivative of mass times velocity. Perhaps you're more familiar with F equals ma, mass times acceleration. Force equals the derivative of mv is a slightly more general equation that applies when mass is not constant. Notice that if mass is constant, you can take it out of the derivative and you're left with ma, because dv dt is a. But this is a more general equation for when the amount of mass we have is not constant, such as in the rocket problem and in this falling rope problem. So rho gx, the force, is equal, and we just apply the product rule here. But what's dm over dt? Dm over dt is the rate at which the overhanging rope's mass is increasing, which is just the density times the rate at which the length is increasing. So dm dt is just rho dx dt, or another way of seeing that is just, since m equals rho x, if you take the derivative with respect to t of both sides, you get dm dt equals rho dx dt. And then this one's pretty straight. Well, oh yes, well m is just rho x, so I again just substituted that here. I divide through by rho, so this is good. It turns out that rho, the density of the rope, does not affect this problem. So we just divided through by rho, and we now know that we have this differential equation. And this is a system of equations. We know that velocity is the derivative of x with respect to t, and then we have this equation, and this is a nonlinear differential equation that I haven't taught you how to solve. So we're going to go ahead and use a computer to solve this system of equations. I put it in a box there. So the solution to our system, which I'm calling SolSys, equals, and then we do a numerical differential equation solve, where we give a comma-separated list of our differential equations and our initial values. It does not matter what order you enter these. Then you declare what your dependent variables are. So x and v both depend on time, and I want a solution as time goes from 0 to 20 seconds. I figure surely the rope will have fallen off in 20 seconds, so I thought 20 was safe to put in as my upper bound. And then we can extract our answers for x, and xSol, this is the function that was found. I just take x, where I use the answer that was found in SolSys, and that's my function of time. That's the answer to the problem, basically, is it's x of t. And then I just set x of t equal to 4, because I want to know when exactly 4 feet of rope have fallen off the table. So I set my xSol equal to 4 and solve for t to find that t is 0.54. So it takes just over half a second for the rope to fall off the table. So it turns out we can solve the problem on the previous slide, but you have to be careful because the solution is extremely clever. In fact, it's face-meltingly clever. So here we go. So gx is equal to v squared plus x dv over dt was the differential equation we found. Let's rearrange it like this. And we did this in a previous problem. I believe it was the moon landing problem. I think it was two videos ago, where dv dt is dv dx, dx dt by the chain rule, and then dx dt is just v, so we can make this substitution dv dt equals dv dx times v. And when we make that substitution in here, we get this differential equation. And this is still pretty hard. I can't explain to you why to do this, but we will. I multiply both sides by x, and I'm going to tell you right now that I can't explain why we do that, except that something wonderful happens. So let me tell you a little bit of philosophy about solving differential equations. Sometimes multiplying a differential equation by something makes it solvable. And whenever that happens, this is called an integrating factor. Now, I taught you about integrating factors for first-order linear differential equations. Well, it turns out that we can often find integrating factors for other equations. I'm not going to teach you what rule I used to find this. It has to do with what's called exact differential equations. If you want to look it up on Wikipedia or something, you're free to. But I don't plan on covering it in this course. I just want you to be aware that this technique exists. So you can multiply certain equations by integrating factors, and then it allows you to rewrite the left-hand side. So I leave it to you to check that if you use the product rule and chain rule of differentiation, the derivative of all this is equal to what you see here. Now we can integrate both sides, and we can now solve this differential equation. Just solve for v, actually. First of all, since v is 0 when x is 1, that's because when the rope is hanging over the table by 1 foot, the rope was at rest. We find that you plug this information in here, you find that c is negative g over 3, which is negative 3.27. Now write that v is equal to dx over dt, and this expression here becomes this. This is a separable equation, so we can just solve it for dx over dt. Oops, sorry. So dx over dt is all of this stuff. And if I separate variables, so I bring all the x's over to the left-hand side and bring the dt over to the right-hand side, we get this. And so let capital T be the moment in time when the rope has fallen off the table, that is when x equals 4. And so we know that x of capital T equals 4. So if we integrate from x equals 1 to x equals 4 with respect to x, that's this on the left-hand side, that's the same as integrating from t equals 0 to t equals capital T on the right-hand side. I can put a more detailed explanation for that online, or we'll go over it in class. Yes, it turns out that if on the left-hand side you have an expression that's with respect to x, and on the right-hand side you have an expression that's with respect to t, then you can integrate with respect to certain values for x, and that's the same as integrating using the corresponding values of t. So t was 0 when x is 1, and t is capital T when x is 4. So this is allowed. It follows from the chain rule, the U substitution formula for integrals. You can refer to a calculus textbook for the U substitution formula for definite integrals, and you'll see that this is allowed. So so the right-hand side is just root 2g over 3 times capital T. So we can divide both sides by root 2g over 3, and we get that capital T is equal to what you see here. And then I just evaluated this by computer to get 0.541 seconds, which is the correct answer that we got on the previous slide. Note that g is 32 feet per second squared because we are dealing with feet instead of meters. So in the last two solutions we use Newton's law. F is the derivative with respect to time of mass times velocity. What if we tried using conservation of energy? That the initial potential energy plus the initial kinetic energy equals the potential energy plus the kinetic energy at any time t. So let's say that the table is at height 0, and that means that if the rope falls down, then it's considered to have negative potential energy because it's at a negative height. And let's compute the potential energy of the rope when a length x is hanging. So the total potential energy of the rope is equal to the potential energy of the rope sitting on the table plus the potential energy of the rope that is hanging. But we declared that the table was at height 0. So the potential energy of the rope on the table is just all this times 0. The rope hanging, however, has a mass of rho gx, and its height, or its average height, is negative x over 2. The way you can think about that is that if you have rope hanging off the table, the rope at the top, here, let me get my pen. Here's your table, and you have rope hanging off the table, a distance x, and the center of mass of the rope is at a distance of x over 2. I'm using a mouse pad here, so please excuse me. But we can consider the hanging part of the rope to be a mass at mass right here. So if the rope is hanging off a distance x, then the height of this rope can be considered to be x over 2, except it's x over 2 below the top of the table, so it's negative x over 2 is our height for our potential energy calculation. So we end up with minus rho g over 2 x squared for our potential energy. For kinetic energy, the rope on the table is at rest, so it doesn't have any kinetic energy either. But the rope that is hanging off the table is falling at velocity v. And so the kinetic energy is, well, the rope on the table has 0, and the rope that is hanging has kinetic energy equal to 1/2 times the mass times the velocity squared. That's the formula for kinetic energy. I'll write that down in case you've forgotten. Kinetic energy equals 1/2 mv squared. That was not bad considering that was with a mouse pad. So yeah, that was that. And by conservation of energy, potential energy plus kinetic energy ought to be constant. So, and since the initial energy of our rope is, well, it was at rest, so it didn't have any potential energy, but it didn't have any kinetic energy, but its potential energy was minus rho g over 2 times 1 squared. So this was our initial potential energy. And so minus rho g over 2 is the initial energy, so it has to be the energy always. So we have this equation relating x and v. We can solve for v, and we get, let me erase that now because it's in the way. Great. And we have, so I solved for v, and then noted that v is the same as dx over dt, and we get this expression. And we just bring all the x's over to the left-hand side and all the t's over to the right-hand side, and we get this. And again, we can integrate from 1 to 4, integrate from 0 to capital T, where capital T is the moment that the rope falls to 4 feet. And so we have this. The right-hand side is just root g times capital T. So we can solve for capital T, 1 divided by root g times this integral. And we conclude that capital T is just less than half a second. So hold on a second. When we used this law, the conservation of momentum, we found that the rope falls off the table in a little bit more than half a second. But when we used conservation of energy, we found that the rope falls off in a little bit less than half a second. So what in the world is going on? I will leave you to ponder why we got 2 different answers and to figure out which answer is correct. However, I don't recommend doing an experiment. I don't see that being very feasible.